This video aims to explore the maxima and minima of functions. How do we work them out, not only algebraically, but how do we look at them and analyze them through the function's graphical representation for a bit more intuitive insight. These maxima and minima are turning points in the function. So we can see at the very top right hand side here, I have a stationary point is equal to the derivative of y with respect to x equals 0. As we know from our differentiation videos that when we get the derivative of a function, we're getting the tangential slope of that function at a particular point. So the stationary points that we're interested in are going to be the local maximum and the local minimum of these functions. So before we get into looking at our example here, we're just going to look at these two little diagrams here. This x arrow is just essentially saying the x-axis is increasing from left to right in both of these graphs. So we can see here that we have a function f of x in blue, and when we take the derivative of this function and we let it equal to 0, we can find where that graph has a turning point. So we can see here that the f of x is increasing its f of x value as x increases, then it hits a maximum, hits a local maximum here, and then it starts to decrease. And at this point you can see that the slope is equal to 0. So there's no increase of f of x as x increases. Then we have the total opposite here, where we have once again our x is increasing left to right, but then we have another f of x that's decreasing, and then it hits a turning point, a local minimum, and then it starts to rise again. But without this graphical representation, you could say that, well, how would we know without viewing these the nature of this function, because we know that the derivative of the two functions is the same when we're looking at the turning points. They're both equal to 0. So that question will be answered when we work through this example here. There's a certain part in the procedure where we look at determining the nature of these stationary points, the local min and local max. So halfway down the example, you'll see that there is a method in which we can determine the nature of the f of x turning point. Right, so the first question that we're going to ask is, with our function here, where are these stationary points? Well, we've seen at the top here that we find them by differentiating the function and letting it equal to 0. So we're letting the derivative equal to 0, and then we're going to solve for x, and that will tell us where these turning points, where these stationary points are located. So that's what we're going to do first. We're going to find the derivative of this function. So if you're not too comfortable with the differentiation, I have a few videos previous to this that you can have a look at. Alright, so the derivative of this minus 9x will just go to minus 9. The plus 6x squared will go to plus 12x, and the minus x cubed will go to minus 3x squared. And not to forget the equal to 0. Right, so I'm just going to multiply across by minus 1 and reorder this function. So that's going to be, I got the squared at the first expression here, and multiplying across by minus 1, this is going to change to minus 12x, and this is going to change to positive 9. So if you can take maybe 30 seconds and just try to recognize that our stationary points are defined as a derivative of the function equal to 0. We've found the derivative of our function and we've let it equal to 0. So this here is going to tell us where we find these stationary points once we determine our x values, and then we can plug that back in and we can get the corresponding y values. So it's going to tell us where these points are. So then I see that there is a common factor here, so I'm just going to divide across by 3, which will give us an x squared minus 4x plus 3 equals 0. And then this is going to be factorizing, it's going to be x minus 3, x minus 1 equals 0. So as we know how to finish this off. We know that x is equal to 3 from this factor, and x is equal to 1. Alright, so where are we? Well, we have found the x values of this function where the stationary points are located. Now what we have to do, of course, if we have an xy graph, it's not enough just knowing the x values, we have to know the y-axis as well, so we can actually pinpoint a location as to where this stationary point occurs. So to do this, we have to insert each x value back into the original function. So you're not inserting it into derivative, you're inserting the values into the original function. So first we'll do x equals to 3. I'll just do in a different color to make it clear. Right, so f when x is 3 is equal to 2 minus 9 by 3 plus 6. Then that's 3 squared minus 3 cubed. This is equal to 2 minus 27 plus 3 squared is 9 by 6 plus 54. 3 cubed is 27 minus 27. That equals, the minus 27 will then cross with the positive 54, leaving us with a 2. So our f of 3 is equal to 2. So in other words, our first turning point is located at the position y equals 2 and x is equal to 3. So now we're just going to find the y value when x is equal to 1. So then our f of 1 is going to equal, plugging it into our original function, we have a 2 minus 9 by 1 plus 6 by 1 squared minus 1 cubed. So that is equal to minus 2. So we've now determined where these stationary points are with our function. There's one located at 1, minus 2, and also at point 3 and 2. But the next question then is to determine the nature of these stationary points. Because if you recall at the very beginning, we have essentially found the point of these stationary points, but then we don't really know the nature of the surrounding f of x function in terms of, is it going to be a local maxima or a local minima. So we're now going to work through how do we determine if it's a local max or a local min by looking at a second derivative. So now we're ready to determine the nature of each of these stationary points. The way that we do that is we take the second derivative of our original function. So the first one here, if you remember before, our first derivative here is given by minus 3x squared plus 12x minus 9. So our second derivative is just this function differentiated, which is going to be a minus 6x plus 12. So that's our f double prime here with respect to x. So what we do from here is we use the x value of each point and we insert that into the second derivative, and we then would analyze the result after, which we'll go through. So then we're going to plug in our f prime, our x is 1, so that's equal minus 6 by 1 is just minus 6 plus 12 is going to give us a value of 6. And then our second one, so this is when x is equal to 1, and our second x value we have to deal with is 3, that's the second turning point. And then that's going to equal minus 6 by 3 is minus 18, plus 12 is going to be minus 6, and that's where x was equal to 3. Now we're finally ready to determine the actual nature of these stationary points. We have to analyze our two results when we inserted the x values of each point into the second derivative. You can see that the first one gave us a positive 6, and I've written two rules over here. If the second derivative, when the value is inserted in, turns out to be greater than 0, which it is for our first example, that is a local minimum turning point. And then conversely, if the value is a negative number, as we have here, which is a minus 6, that would signify a local maximum in the function. So then we see here that our results are turning point 1 minus 2 is a local minimum, which looks like this second diagram over here. And our second turning point, 3, 2, is a local maximum, which will look something like this. So this here is the graphical representation of our function f of x, done up just by plugging in x values, getting corresponding y values and plotting it accordingly. You can see that it matches up with what we have found throughout the video. When I first plotted the turning point, the 1 minus 2, you can see here, and then I plotted the 3, 2, which was our second turning point, and it's a continuous graph, and when I connected the points and drew the graph, you can see that we do indeed have a local minimum at turning point 1 minus 2, and then this increases to a local maximum at point 3, 2, before it then tends off towards down this direction, negative infinity. So this is a nice way of verifying your work to make sure it seems correct, because as we can see, if we just looked at this, it's quite straightforward to say, yeah, that's a local min, that's a local max, but then verifying it through either the algebraic way, working it out through the derivative, the second derivative, and then seeing it match up with a graphical representation. It's just nice clarification that you are indeed correct. So I hope you enjoyed the video. This was an introduction to finding the local minima and maxima and determining the nature and working with them. If you enjoyed it, if you could like and subscribe and hit the bell so you know when the new video comes out, that'd be great.